Good morning, students. Myself, Mrs. Shalini Singh, Senior Assistant Professor, School of Pharmacy, BBD University. Today, I am going to discuss the topic Conformational Isomerism. Contents are understanding conformational isomerism in ethane, conformational isomerism in N-butane, and conformational isomerism in cyclohexane. Conformational isomerism is a form of stereoisomerism in which the isomers can be interconverted just by rotations about formally single bonds, while any two arrangements of atoms in a molecule that differ by rotation about single bonds can be referred to as different conformations. Conformations that correspond to local minima on the potential energy surface are specifically called conformational isomers or conformers. Conformations that correspond to local maxima on the energy surface are the transition states between the local minimum conformational isomers. Rotation about single bonds involve overcoming a rotational energy barrier to interconvert one conformer to another. If the energy barrier is low, there is free rotation, and a sample of the compound exists as rapidly equilibrating mixture of multiple conformers. If the energy barrier is high enough, then there is restricted rotation. A molecule may exist for a relatively long time period as a stable rotational isomer or rotamer. While there are an infinite number of conformations about any sigma bond in ethane, two particular conformers are noteworthy and have special names. In the eclipsed conformation, the carbon-hydrogen bonds on the front and back carbon are aligned with each other with dihedral angle of 0 degree. In the staggered conformation, the carbon-hydrogen bonds on the rear carbon lie between those on the front carbon with dihedral angle of 60 degree. As we can see in the given picture, when an ethane molecule rotates about its carbon-carbon single bond, two extreme conformations can be result, the staggered and eclipsed conformation. Here, we will discuss Newman projection to discuss the conformation. When two carbon-hydrogen bonds are brought into a dihedral angle of 0 degrees, their electron clouds experience repulsion, which raises the energy of the molecule. The eclipsed conformation of ethane has three such carbon-hydrogen eclipsing interactions, so we can refer that each eclipsed carbon-hydrogen costs roughly 1 kilocalorie per mole. The lowest energy conformation of ethane is the staggered conformation. All of the carbon-hydrogen bonds on the front carbon are positioned at an angle of 60 degree relative to the carbon-hydrogen bonds on the back carbon. This angle between a sigma bond on the front carbon compared to a sigma bond on the back carbon is called dihedral angle. In this type of conformation, the distance between the bonds is maximized, and maximizing the distance between the electrons decreases the electrostatic repulsion between the electrons and results in a more stable structure. If we now rotate the front CH3 group 60 degree clockwise, the molecule is in the highest energy, that is eclipsed conformation, and the hydrogens on the front carbon are as close as possible to the hydrogens on the back carbon. This is the highest energy conformation because of unfavorable electrostatic repulsion between the electrons in the front and back carbon-hydrogen bonds. The energy of eclipsed conformation is approximately 3 kilocalorie per mole, means 12 kilojoule per mole, higher than that of staggered conformation. Now come to the conformational isomerism in N-butane. The structure of butane is represented by Newman projections below by designating the two middle carbons, one as the front and one as the behind carbon, and the connecting the two end methyl groups accordingly. When we look at the chemical structure of butane, we can see that it has two substituents, which are methyl groups attached to the two end carbon atoms. The methyl group is comparatively larger than hydrogen atoms. However, we can also see that everything on the front side is eclipsing with the structure on the back side. One methyl group is present in front of the other methyl group, and the other hydrogen atoms are kept at the back of other hydrogen atom. In short, the structure is completely eclipsing or they are fully eclipsed. Butane is an alkane with the presence of carbon-carbon single bond. Normally, we rotate the molecule of butane at the axis of carbon-carbon single bond. It shows different conformation isomerism. Generally, butane has four conformations, which are fully eclipsed, gauge, eclipsed, and anti-butane conformations. Now, if we rotate the front methyl group by 60 degree, or when the dihedral angle is 60 degree, then there is a formation of gauge or staggered conformation, as we can see in the picture. It basically has the presence of identical groups at 60 degrees from one another. This type of conformation is more stable as there is a little hindrance between the same molecules. If we make the dihedral angle 120 degree, then this form of isomer is also known as eclipsed conformation. However, this eclipsed form is quite different from the previous fully eclipsed state. The basic difference is that the methyl group is eclipsing the hydrogen atom and not the methyl group. On rotating the isomer at an angle of 180 degree, the two methyl groups are found lie exactly opposite to each other. This conformation is known as staggered conformation or anti-conformation. Usually, each conformer is also interconverted to the same forms by rotating the isomer around the center carbon single bond. Eclipsed conformer can be converted back into gauge conformation by rotating it 60 degrees. And when an eclipsed is rotated by 180 degree, it forms anti-conformer. Rotation of anti-butane by 120 degree again leads to the formation of gauge conformer. So, if we give ranking to the conformations of N-butane according to the energy level, the ranking order will be: first one is anti, second gauge, third eclipsed, and fourth one will be fully eclipsed conformation. This can also be visualized using an energy diagram. Cyclohexane is a cycloalkane which is an alicyclic hydrocarbon. It is colorless with the molecular formula of C6H6. It consists of a ring of 6 carbon atoms that is flammable, and cyclohexane has two non-planar puckered conformation and both are completely free from strain. These are called chair form and board form. Because of their shape, there are so many examples of common cyclohexane conformations such as chair form, board form, twist board form, half chair conformation, and the naming of the molecule is based on their own shape. A regular hexagon shape contains internal angles of 120 degree. However, the carbon-carbon bonds belonging to the cyclohexane ring have a tetrahedral symmetry with the bond angle corresponding to 109.5 degree. This is the reason why the cyclohexane ring has tendency to take up several conformations. As I told earlier, that common conformations of cyclohexane includes the boat, the twist boat, the chair, and half chair conformations, which are named based on their shape. Now come to the first conformation of cyclohexane, that is chair conformation. If two carbon atoms on opposite sides of the six-membered ring are bent out of the plane of a ring, a shape is formed that resembles like a beach chair. This chair conformation is the lowest energy conformation for cyclohexane with an overall ring strain of 0 kilojoule per mole. In this conformation, the carbon-carbon ring bonds are able to assume bonding angles of 111 degree, which is very near to the optimal tetrahedral angle, that is 109.5 degree. So angle strain has been eliminated. The chair conformation cannot be formed without changing the bond angles or bond length. We can think of it as two chains, mirror image of one of the other with opposite dihedral angles. The distance from atom 1 to atom 4 depends on the absolute value of the dihedral angle. If these two dihedral angle changes, as it is not possible to maintain the correct bond angle at both carbon 1 and carbon 4. Now come to the next conformation of cyclohexane, that is Bode conformation. The Bode conformation of cyclohexane is created when two carbon atoms on opposite sides of the six-membered ring are both lifted up out of the plane of the ring, creating a shape which slightly resembles like a boat. The Bode conformation is less stable than the chair form for two major reasons. The Bode conformation has unfavorable steric interaction between a pair of 1,4 hydrogens, that is also called flag pole hydrogens, that are forced to be very close together. This steric hindrance creates a repulsion energy of about 12 kilojoule per mole. Now come to the next conformation, that is twist Bode conformation. The Bode form is quite flexible, and by twisting it at the bottom created the twist Bode conformer. This conformation reduces the strain which characterize the Bode conformer. The flag pole hydrogens move further apart. The carbons, they are attached to are shifted in opposite direction. One is shifted to forward direction and another is back direction. And the 8 hydrogens along the sides become largely but not completely staggered. Though it is more stable than the Bode conformation, the twist Bode conformation is roughly 23 kilojoule per mole less stable than the chair conformation. Now come to the next conformation of cyclohexane, that is half chair conformation. Cyclohexane can obtain a partially plane conformation called half chair, but with excessive amount of ring strain. The half chair conformation is formed by taking planar cyclohexane and lifting one carbon out of the plane of the ring. The half chair conformation has much of the same stream effect predicted by the fully planar cyclohexane. Overall, the half chair conformation is roughly 45 kilojoule per mole and less stable than the chair conformation. So it is all about the conformational isomerism in ethane and butane and cyclohexane. Thank you, students.